Okay, I hope, let's see how many of you are there. Okay, quite a number now. So, um, so this is your rotor stages and this is your stator stages. Okay, so we'll see the working of it. So this will be represented like this. I think I should have taken the image. Okay, here again. So in this image, this is an isometric view, correct? But if you look at in the front view of this image, it would be something like this. This will be your rotor stage, and then your stator stage. No, first one would be your stator stage, and then rotor, and then rotor, and then stator. Okay, we'll just take two for now, and then call it rotor and stator. And this is one blade. Some random drawing I'll do, just don't take it to be the exact one. Okay, so these are the blades. So blades are nothing but your airfoils, correct? So these are the blades, or rotor blades, and correspondingly you'll have your stator blades. So this image, if you look at from this side, from the front view, you'll see something like this, correct? So that will be your first stage, will be rotor, and your second stage will be stator. Okay, so rotor meaning it can rotate, and stator is stationary, it is not rotating, correct? So like this. So for this one stage, when a gas is coming in this direction, or any fluid is coming in this direction and coming out from here, the maximum compression ratio you can have at these 2 points is 1.5. Okay, so similarly, if you multiply these stages like this, you can have n number of casing, and that is why you have this many numbers. So this has got one, so one stator blade and one rotor blade will encompass as one compressor stage. So 1 2 3 4 5 6 7 8 compression stages are there in this. Okay, so again 1.5 is quite generic. I think right now, because of the technological advancement, this number could be more. Okay, but know that it is not much more as the centrifugal compressor, but it can be higher. Okay, so now what is the idea behind this, or how does you compress, or how does this work? Let us see with so again the same thing what I've said so far. So rotor is attached on the shaft, and stator is actually attached on the engine casing. Okay, from the front view you'll observe like this, and once you see the stages like this, you call this as, I mean, whenever you see a blade like this from the front view, if you observe it in aligned like parallelly like this, you call it as cascade blading. Okay, very important word for you to understand. If you see an arrangement of blades in one column, in one such column like this, or one such column like this, you call this as a cascade of blade. Okay, so probably if you see, this one column, one section of it, if you remove, you call it as cascade blading. This is like cascade blading. Why is this important? This is important because if at all you want to derive something, see, this is cascade blading. So if at all you want to derive something, let us say you want to derive what is the amount of lift that is being generated between these two blades, correct, and the overall lift So lift here is nothing but compression. Okay, if it was in air, it would have been giving lift. Since it is encompassed in one body, here it would be compression. So if you want to understand what is the amount of lift that is being generated, you can't calculate everything at once. So what you do, you open the blade, that is, let us say if this is your circular axis, what you'll do, you'll cut this portion. So you'll cut this portion and elongate it. So if you open it, it will be like this. Therefore, now your blades will form a cascade like this. So once it forms a cascade, you only do analysis on two such blades. So this one blade and another blade. So it will be like this. Correct. So I think here, if you want to visualize, it would be something like this. So okay. So something like this. So if you open and keep it, you'll get what is known as a cascade. So when you want to analyze the overall effect or overall thrust or compression ratio that is being produced by this particular compressor, what you do, you take two successive blades and then apply whatever equations, be it Bernoulli's, be it whatever lift equation or drag equation, whatever you want to do, or the physics behind it, you apply just to these two sections, and then you integrate it throughout the compressor. Okay. So integrate it throughout the compressor. So therefore, whenever you're doing any analysis also, if you are doing any ANSYS analysis or if you're doing any fluent analysis, you don't take the whole compressor itself, because again the calculation time and the run time will all increase. So to avoid that, you'll just take one cascade and then find out. See again, so see here also, if you can see, if you just take probably I'll just show you like cascade blading ANSYS. See, so your whole compressor, you just limit it to a small portion and then perform your analysis. This is flow analysis. So if you see like where the lift is being generated, or if you can see, so velocity contours. Okay, so rather than doing this, okay, this will take a huge amount of time to calculate and then obtain your results. So they have done for the whole compressor. So to avoid this, you'll take only a small portion of it and call it as cascade, and then define your geometry and then obtain the results. Okay, so that you know as cascade. Now next we'll see, okay, how exactly the compression portion compression is happening. So the axial is made up of series of rotating airfoils such as rotor blades and stationary blades or stator blades called stator vanes. Okay, as its name implies, the air is being compressed in a direction parallel to the axis of the engine. So axis of the engine, what is the axis of the engine? The axis at which the shaft is located. So if the shaft is in this direction, the compression is also taking place in this direction. So therefore you call it an axial compressor. So this is the axis of the compressor, correct? Central axis of the shaft and the overall engine. So if the compression is taking in this direction, you call it axial flow compressor. Okay, the entire compressor is made up of series of alternating rotors and stator vanes, which stage constructed. Okay, some axial flow have two or more compressors or a spool driven by separate turbines. So I've already discussed you many times what is a spool. One set of compressor blades will have one set of turbine blades. So a rotor and stator will have one turbine. You call it as one spool, correct? And many things you call it different spools. And compressor therefore free to rotate at different speeds. So when you have spool, we've discussed in class already. So if you have another spool, there will be a shaft inside shaft. So therefore the high speed will rotate at higher speed, and by some gear mechanism, the lower turbine, the lower compressor will rotate at different speeds. So that is what they're saying. In addition to small vental area created by type of compressor leads to itself installation in high speed aircraft. Unfortunately, okay, this is the major drawback of axial flow compressors, the delicate blading. especially towards the rear, makes this type of air pump especially susceptible to foreign object damage. Okay, so even because they are rotating at very high speed and this force is axial, so if some foreign object, let us say a small stone, will come and hit the blade will be immediately damaged, and that damaged blade will cause a series of damage within the compressor and the engine itself. So therefore you have this study called bird strike. Okay, I think you have heard it. So bird strike, this study, so if you can see these images, it has occurred on some of the major portions. Importantly, bird strike is most susceptible or most vulnerable to the engines. Okay, so when this engine failure will occur because of bird strike, so therefore this is another field of study especially done for axial flow compressors. So birds flies for engine. I think there is a very good video also. Probably if you can see this video.
It's an incredible sight. Danger, literally. They cause.
So you can see here how the blades have been damaged. So this is one of the major drawback in an axial flow compressor. While a centrifugal compressor can handle any foreign object, any sand particle or any smaller stones going inside the compressor very easily. So therefore, if you can see your own very own motor, hydraulic motor, the water motor that you use is a centrifugal motor actually. So centrifugal hydraulic motor. So your water will not just be water, it will be a lot of things. It will be mud, it will be sand particles and all those things. So in spite of that, it does not face such severity because the direction it comes is not axial completely. So in a centrifugal compressor, it will come axially and exit tangentially. Correct. So because of this configuration, the the foreign objects whichever come will easily move or tend to move in a direction away from the blades and in between the blades. But in this case, it is not. So therefore, it has to move through the blades. So that is why it is one of the major reasons. I think one example we can see. These are some of the compilations actually. So let's see one. Okay. Anyways, so we'll leave at that. So now, how exactly is the compression taking place? So, what happens? Your fluid, whatever, will come at some velocity. Once it has come in some velocity, your blade is moving in a velocity u. Correct. So since it is moving in a velocity u, and here there is some work transfer occurring. Since it is rotating on the stream of air, the rotor will add work, dou W. The rotor will add energy to your stream of air. So by adding, so what will happen? There is increase in kinetic energy for the stream. So plus Ke. So this stream kinetic energy is being added. So once it is coming out, it will come out at a velocity much higher. Okay. But what does a stator do? A stator will convert this kinetic energy to static energy or static pressure. I think the better word could be called as pressure head. Head pressure or pressure head. So the idea is simple. The rotor will add the kinetic energy. The stator will convert the kinetic energy into pressure, static pressure. So once it is coming out of this, it will now be at a lower velocity but at a higher pressure. Okay. So the same thing happens in all of the stages, and thereby your pressure is getting increased. So one may question, okay, why just have stator and rotor only? So if I'll have a rotor stage, so this is a rotor stage. If I can just have a series of rotors like this, okay, just know this, only rotor is adding work. Stator is not doing anything. It is simply acting like a diffuser. It is simply acting like a diffuser and converting the velocity into static head or static pressure. So if you have a series of rotors like this, so you may expect the velocity to increase, and it must increase ideally. Correct. So it must increase ideally, but the drawback is, since the rotors are rotating, I think I'm not sure the exact word to it. What is that? Vertosity or the vortex, basically. So the flow will not be linear. It will induce a very huge turbulence within the rotors. So if you don't have a stator stage, velocity will increase. Okay, velocity will increase, but the vertosity or the vortex or turbulence will be very huge. And since the velocity is huge now, so this is your absolute velocity, correct? So if green line is your absolute velocity, V, and red line is your velocity of the blade. So red line is your velocity of blade, U, and then let us say same type of U. So U probably U1 and U2 and so on. So if you have this and you have given view, so like I said last time, what is the third vector between U and V is your relative velocity. So that relative velocity will be very huge. So if your relative velocity is very huge, and controlling that system is also very tough, and it is, one second, I'll just draw this. Correct. So this is for the overall rotor stage, and this is your V, and this is your U, and this is your relative velocity VR. So what happens, even though your absolute velocity is increasing, because of the vertosity and the blade velocity, your VR also increases. Okay, if you have VR, that means your V will decrease. Your absolute velocity is decreasing and your relative velocity is increasing. If your relative velocity is increasing, that is of no use to you. Okay, you have to keep, so if you keep your relative velocity minimum, see if this line is minimum, so if this line is only about so much, okay, if it is only about so much, automatically your green line will increase in its length. Okay, so I can't show you the variation, so it will be something like this. So it is like a triangle. So if one component is increasing, the other will decrease. Correct. So that is how it works. So therefore, just by having the rotors, you can't run it, and also the adverse kinetic energy on the blade will have impact on the overall system. So therefore, it is mandatory to have a rotor and stator system for an axial flow compressor. Understood? So we'll see some of the advantages and disadvantages. Axial flow compressor have the following advantages: high peak efficiency. So compared to your centrifugal compressor, the efficiency of an axial flow compressor is very good, and small frontal area for a given airflow, which we already discussed, and straight through flow allowing high ram efficiency. So since the flow is always axial, unlike your centrifugal, where I said it will enter axially and it will exit radially. Correct. So since that is missing, you'll also make use of ram efficiency. So ram efficiency is striking directly on the blade or striking within the component. So once it is coming inside, ram efficiency is nothing but your external, something like your external and internal compression. So in your external compression, because of the geometry of the compressor itself, there is some compression going on other than the compression what is happening in the blade. Okay, so that is ram compression. And then increased pressure ratio due to increased number of stages with negligible losses. Okay, so if you take overall, it is actually very good, but the disadvantages is good efficiency over narrow rotational speed ranges. Okay, so meaning to have a very good efficiency, you'll have to operate it in one particular rotational speed. So like how your centrifugal compressor can operate in any other range, it is not the case. To have a perfect maximum efficiency, the rotation of the shaft should be constant. Okay, difficult to manufacture and high cost. So given the design, how complicated it is, the manufacturing cost will obviously go high, and relatively high weight, because when you want to compress it in 30 to 25 or 20 above, the number of stages will increase, so therefore the overall weight will also increase. Okay, high power starting requirements, correct. So since all of the blade should start compressing, so to start it you'll have to use some mechanism, so some power source which can generate equal amount of compression, so therefore high starting power requirements. Okay, so now we'll see the TS diagram for this. Let this be here, and I'll still draw on your okay. So first we'll only see the static TS diagram. Static TS diagram is stating on keeping only static terms, that is your T1, P1, or like I said, two terms. Any equation will follow something called the total. Even in terms of temperature, if I see, it would be total temperature or stagnant temperature will be equal to static temperature plus, in case of temperature, it would be velocity, so it would be Tc square, sorry, absolute velocity, so that will be V square divided by 2Cp. Correct. So this will define your temperature. Your pressure will be like this: static pressure plus the dynamic pressure, half rho V square. Okay, so we'll only plot for static first. So static first, so you have 3 stages. So your one stage will be here before entering to the rotor. So your stage 1 is here and stage 2 is here. Okay, and your stage 3 is here. So in all of these 3 stages, so correspondingly you'll have 3 temperatures, correct. So T1, T2 and T3, correct. So ideal efficiency, ideal compression, isentropic compression will be very straight line like this from 1 to 2. This is T and this is S. Okay, so it is not ideal, therefore actual compression will be like this. So from 1 to 2 like this, and then from 2 to 1 like this. Okay, and the corresponding pressure you measure will be like this. Corresponding static pressure what you measure will be like this. So this will be P1, this will be P2, and this will be P3. Okay, so rotor inlet, so from here, so here it is rotor inlet, at here it is rotor outlet as well as stator inlet. Okay, and at this stage you call it stator outlet. Okay, this is just your what is this, static condition. So with static conditions, okay, and correspondingly if you extend these lines on the static point, so if this line is extended to meet at this point, you'll have your stagnation pressure, and this line you'll have your stagnation pressure here, and the corresponding stagnation pressure. Okay, so then we'll see the stagnation pressure itself. So if you see both the red, so red here is the stagnation point, so that is total pressure and total temperature, and blue is your static pressure. So from T1 to T01, so T1 to T01 is nothing but here. Okay, so if you can see, so T1 is your static temperature, a static temperature to your stagnation pressure. So your T1, if your T0 is a combination of these two. So T1 plus V square, that is C square absolute velocity, divided by 2 into specific heat at constant pressure, is T01. So the actual compression process will occur from here. So from here to here it is isentropic. Okay, why? Because that is there within the system, so therefore this is isentropic. From here to the next temperature T02, the overall, so T02. So why T02 and not T03? I'll let you know. So from T01 to T02, so that is from this stage, so from here to here, you'll achieve a stagnation pressure temperature of T02, correct? But T02 is equal to T03. The stagnation temperature of T02 and T03 is same. Why? Because there is no heat addition taking place in the stator system. Heat addition as in, like I said, you have some amount of work input in your rotor, correct? Rotor has work input. So if rotor is having work input, meaning there is increase in pressure, correct? There is increase in pressure. As a consequence of increase in pressure, there is increase in temperature, but you're not directly adding any heat to it. So therefore it is still adiabatic process and then still increasing temperature. But in stator, the process is adiabatic, but you're not adding any work or you're not removing any work. You're just doing the action of diffusion. Therefore, the temperature whatever you achieve at the end of rotor will be the same temperature, will be the same stagnation temperature at the stator. Okay, will be the same stagnation temperature, but the actual temperature or the actual measurable temperature is not the stagnation temperature. It is actually at the exit is T2 and furthermore it is T3. So this is just variation of pressure. Where did that go? Okay, so one thing, to be able to understand this, I mean, for you guys to be able to understand what is actually going on here, if you know these two equations and the significance of P1, T1 and T0 and P0, you can easily understand this graph. Okay, hope you understood. Any doubts? So rho is changing. Where Tejas? No, I mean, like, what do you mean? Absolutely, rho is changing. Oh, you're saying here half rho v square. So what will happen to this? Correct. I think that is your question. So half rho v square. Yes, flow is compressible, but the one habit that I have most of the times is that these equations, these equations are actually not the direct pressure but specific. So it's not capital P, it is P0 is equal to P1 plus half V square. Okay, so one mistake or one habit that I have is not to see as specific. Okay, I have my own reasons, I don't see it as specific, but in all of the cases, even though it is a compressible flow, you take the specific equation. So it is specific pressure. So therefore, the mass quantity will be will be taken for per unit volume. So when you take that per unit volume, the rho, even though it is compressible, you'll be speaking in terms of specific. So therefore, there is no much change in here. But the actual changes what happen is when the velocity or Mach 1, when it is crossing Mach 1. Okay. So when it is crossing Mach 1, so if remember your diffuser also. So let us let us take case of just consider this to be a diffuser. Even in your diffuser, the equations will follow. I mean, is agreeable. What are the general equations what you follow, and the graph variations is agreeable as far as the inlet Mach velocity is less than 1 and outlet Mach velocity which cannot exceed 1. Okay, so with this condition, okay, so within this limit, your equations or your graphs will follow a common pattern. Once this limit is crossing, even though the flow is compressible, all other parameters come into picture only when this is crossing Mach 1. So even though the flow is compressible, you'll be speaking in terms of specific pressure or specific temperature, which you don't you don't dig around, but it is understood. You're reading it in terms of specific. So when you take it in terms of specific, your mass term will become, will be divided out of it. So therefore, density will not play a crucial role up until the point is that Mach is not greater than 1. Okay. I hope you understood what I was trying to tell. So, okay. So this is specific. Therefore, rho is not there when you are doing it for specific. So now we'll see what is happening to the successive stages. So this is for just one stage while it is passing from rotor to stator. So for one stage we have drawn the TS diagram, but if you look for multiple stages, so ideally speaking, it is all isentropic. So a thick line is an isentropic line. So from first stage in the rotor is isentropic, therefore it is a straight line, and then this is acting like a diffuser. So therefore, no increase in temperature but increase in entropy. Correct? So increase in entropy, and then isentropic again. Therefore, increase in temperature, and in the stator stage, no heat addition and no temperature changes. So therefore, temperature is 0, but entropy 0. So this is how it goes on the multiple stage level. But since it is not ideal case, the rotor will follow a polytropic line, a polytropic adiabatic process. So I think rather than polytropic, you can just say it as adiabatic process. So in an adiabatic process, the line will be slanted, but the stator is still isothermal, so it will go like this. Okay, the increase in temperature, and correspondingly, if temperature is increasing, the temperature is increasing because pressure is increasing. So therefore, in this graph you can easily plot. So if you draw, so these tangents what they are trying to draw, those are the pressure points they are trying to mark. Okay, so in all of these cases, if you take an average temperature, if you take an average line, so this line what you see, it is an average temperature characteristics. So an average temperature across the compressor in any of the different stages can be known if you draw an average line. Okay, so now we'll get into the velocity triangle. I'll draw it here. Okay, so so we'll take the angle at which sorry, your absolute velocity is first. Say for this case, for your understanding, I'll just draw it like this. So your water will enter on the system with an absolute velocity v1, okay, with an angle. I'll draw the angle later on, and then it will meet, your u, correct? So water is entering, sorry, air is entering the system with v1 at a certain angle alpha, and then it will face the rotor velocity u. There is no u1 and u2 here because at inlet and outlet it is same velocity. Okay, why? Because the blade is not increasing in length, it is same and on a common cascade, so therefore u1 and u2 on both the side will still be same, so therefore you can only represent it as u, correct? So now because of these two, what will you have? The consequence of these two, or these two vectors, is your, what is that? Resultant vector Vr1, correct? So this is your Vr1. So this is your inlet triangle. Okay, while coming to your inlet. So but again, Vr1 will have what? It will have its own tangential and radial velocity. So tangential velocity will be like this. So tangential, if you drop it down vertical, is tangential. So from here to here, I'll just draw another line here, so just to differentiate two red line and black line. Okay, so this will be your VW1, and this will be your VF1, tangential and radial. Okay, and then your alpha is only so much. This is your alpha, and your beta will be this, alpha 1 and beta 1, correct? So now this is for the inlet triangle. For the outlet, you'll have your water coming at a certain angle, so same thing again, blue line, so water coming out at a certain angle alpha 1 and u2, and then same amount of u, so again u will be same, correct? And then your reactional velocity, sorry, not resultant velocity of absolute and rotor, you'll have your Vr2, okay, and then its corresponding tangential and axial velocity. Okay, so if you actually look at this, they both look somewhat similar, correct? They both look somewhat similar, and also your u is same, u1 equals u2 at inlet and outlet is u. So if you combine both of this in a single graph, you'll get something like this. Okay, so since u is same, I'll just try to replicate it here. Okay, but the direction of velocities are different. Okay, the way it is entering and way it is going out is different. So therefore, if I draw it in one single triangle, so your red, this is your u, I'll just take a bit thicker. So if this is your u, so firstly you should have your absolute velocity, so that will come. So with respect to this picture, it is like this: absolute velocity c1 or v1 will be like this, and then the absolute velocity, another one is here, c2. Okay, correct. And the reactional velocity to these two is like this, here and here. Okay, so this is your combination of both inlet and outlet triangles. So this will be your u, which is in red, and this will be your c1, that is your v1, and the blue line is your v2. Okay, and this is your vr1, and this is your vr2. So once you have drawn this line, so you need not draw the what is that, you need not draw your tangential and radial velocity, because you'll have too much to take care. So what you do, you just draw one line here. Okay, draw two line here. Okay, and here. Okay, so from this point to this point is your VF1, correct, because V1 and VF1, and this height from here to here is your, sorry, from, okay, so this height is your VW1, correct, and similarly this height to this height is your VW2, and correspondingly from this is here, so here to here is your VF2. Okay, I mean, if it is confusing, you can separate them out like how I did here in the first place. I mean, since U is common, you're just trying to draw it on the same thing to save time probably, or else you can just leave at this point and then you know what is the horizontal length. I mean, this is most important in your turbo machine's point of view, to find the other angles. So if you just draw it like this, and you mark your alpha 1 and alpha 2 and beta 1 and beta 2, it will become simpler because R and W is understood. Okay, the same thing. So hope you got the inlet triangle and outlet triangle. So in outlet triangle, so once it is coming out of it, correct, stator system is not rotating, correct, your stator system is not rotating, so therefore the inlet to stator will be your V2. So this will be your inlet to stator, V2, VR2, VW2, okay, and then U, and then VR2, correct. So this triangle is at this portion and this triangle is at this portion, and that is also equal to the velocity triangle at the inlet of stator. So once it is coming out of the stator, so in your stator what is missing? Your V is missing, correct. So because your V is missing, water will exit at a certain absolute velocity VR, correct, sorry, so it will excite at a certain absolute velocity v3, and your u is missing, therefore your resultant will also be missing. Only remaining portion is your tangential and vertical components of the velocity. So this will only have VW3 and VR2, and then alpha. Okay, why? Because stator is not moving, so therefore u is missing. So when u becomes 0, the resultant will also become 0. The only remaining portion is these two. So therefore you have 3 triangles in an axial flow compressor because of 2 stages. One at the inlet of the rotor, which is given by this, and exit of the rotor, which is also equal to the inlet of the stator, which is given by this, and at the exit of stator you have this. Because it is not rotating at any velocity u, therefore u is completely absent. You have a certain absolute velocity v3. For that absolute velocity you have the corresponding tangential velocity and the radial velocity. Okay, I think we can stop at this point, and then we'll continue tomorrow. There is some derivations. I think all of this is quite repeating to you guys, if I'm not sure. Correct? Is it quite repeating from turbo machines? Or I would like to see it as a revision. Okay, so that you're able to revise it or get better clarity. So if 2 people are teaching the same concept again, so you'll have a different perspective to it, or different way of understanding it and understanding it better. So I like to see it like that. So hope you understood the velocity triangles, and then tomorrow we'll see some few derivations associated with it. Once we complete those derivations, we can directly get into problems. So tomorrow and the day after we'll complete this module, and then we'll only have turbines to deal with. So probably that is about like another 3 class. So once we get it done, your propulsion is over, unless you want to specify on certain anything that you want me to repeat. We'll continue. Okay, we'll stop it, guys. Thank you.